how do we get nicely formatted output with Prolog? Well, most of the time we don't need to do anything special because the top level formats output nicely for us. For instance, if we ask which characters X are in the string ABC, then we get one solution after the other and nicely formatted. So we didn't have to do anything for this output, we only ask for solutions. And we don't have to press space all the time because, for example, in Scryer Prolog, GNU and Trealla Prolog, we can ask for the first solution and then press A for all solutions. And this comes in handy, especially when there are many solutions, even infinitely many. And one nice aspect of top-level answers is that, at least ideally, they are Prolog terms, and therefore easy to reason about with Prolog. For instance, this is simply a disjunction of equality constraints. So we can, for example, take this answer and paste it back as a query. And we can easily express test cases for such answers, again as Prolog terms. And we can easily reason symbolically about such terms. And it's worth striving for this. We want to be able to reason about all aspects of our programs, including the output of our programs. And therefore, we don't just write output on the terminal, because if the output appears only on the terminal, then we can't easily reason about it with Prolog. Instead, we declaratively describe the output we want to emit, and only then emit it, as the very last step. And Prolog is very well suited for this approach, because Prolog ships with a built-in grammar formalism, definite clause grammars, DCGs, and they let us describe text and therefore also output. So what we do is we describe the output we want to emit as a string, that is a list of characters. For instance, if we want to emit hello world, then we define a DCG non-terminal, let's call it output, and we say this non-terminal describes a list of characters, namely hello world, okay? And we use the predicate phrase to invoke the DCG. For instance, we can ask, what is the list C's described by the non-terminal output? It's the string hello world, exactly as defined. And in this way, we can easily write test cases also for the output, because the string we describe is available as a Prolog term. So that's good. However, we have a problem, because what if the output is not fully known statically, but contains, for example, numbers or other Prolog terms which are computed dynamically and still ought to be part of the output? And to repeat, the best approach is, of course, to simply let the top level print these numbers. Because if we define, for example, a predicate solution, then the top level automatically prints the solution, which can be a number, as in this hypothetical example. But sometimes we want to emit solutions in a specific way, in a way that's different from how the top level prints it. So we sometimes want a formatted solution where we, for example, want to emit a number as part of a text. And we can do this, of course, with a DCG, because we can, of course, convert a number to a list of characters and then use these characters in the description of the text we want to emit. However, doing this is awkward, because we don't want to have to refer to numbers in such a complicated way. What we want is a way to more easily embed numbers and also other Prolog terms in such declarative descriptions of text. And this is where format underscore comes in handy, because it formats your hard disk. Nah, I'm just joking. Format underscore is a non-terminal that lets us describe formatted output, or rather formatted strings. And format underscore takes two arguments. First, a format string, and second, a list of arguments. And as mentioned, format underscore is a non-terminal, so we use it in a DCG or with phrase. And it describes a list of characters. So this holds if and only if the string C's is formatted according to format string and arguments. And the format string, the first argument, specifies the shape of the described list of characters, which means that its characters are used literally, save for control sequences which all start with a tilde, this wave symbol. So, for instance, if we have a format string that doesn't contain a tilde, such as the string hello, and we specify no arguments, and then ask for the string C's that is being described here, then we get C's is the string hello, exactly as in the format string itself. So in this case, the described string C's is identical to the format string. Now, the really interesting feature is that with these control sequences, we can refer to terms from arguments and include them in the described string. For instance, if you have a format string such as the answer is, which is used literally, and then say $d and end the string, then this control sequence $d refers to an element in the second argument. For instance, if the second argument is a list with a single element, the integer 12, and we ask again for the described string C's, then we get a solution, the string, the answer is 12. So the nice thing here is 12, which at the time of the call was only available as an integer, is now, in a sense, embedded in the string as a list of characters. And we didn't have to manually use number jars or anything like it to get this translation. We simply specified the shape of the output as a format string, and with control sequences, we can include terms in this output. And there are several control sequences, such as $d, which we've just seen. This uses the next argument, which must be an integer, $s, to use the next argument, which must be a string, and $q, to use the next argument formatted as by write q. And these are some of the most frequently used control sequences. So for instance, we can describe a string that says a certain number out of a certain total number of entities, which are specified as a string, are here. So this is the shape of the output we want to describe, specified as a format string. And in the list of arguments, we can specify these numbers and entities. And these terms would usually arise as part of the computation or maybe be read from a database and so on. And we are asking for the string C's, where these arguments are plugged in, so to say, at the specified places. So for instance, in this case, we get a solution, the string 5 out of 8 students are here. So we see that each of these control sequences has taken the next argument from left to right and used it. And a few control sequences also take arguments themselves. And sometimes these arguments are optional. For instance, $n means that at this position, a new line character occurs in the string. And it can be used with an optional argument, an integer n, which means that n new lines occur here. Or as another example, nr means that the next argument, which must be an integer, is formatted in radix n. For instance, we may ask for the binary representation, that is base 2 of an integer like this. So this is the same integer in binary. So format underscore is sometimes useful to reason about different representations of integers. And we can use base 16 for the hexadecimal representation, where lowercase letters are used for digits greater than 9. And we get uppercase letters if instead of a lowercase r, we use an uppercase r, like this. And in this case, if n is omitted, then it defaults to base 8, that is octal. And we can also use $* to use the next element from arguments, which must be an integer, as the numeric argument. So we don't need to hard code a numeric argument in the format string, but can also specify it as an element in the arguments list. Then $i means to simply ignore the next argument. And if we want an actual tilde in the described string, we write $, okay? So these are some of the most commonly used control sequences for integers in various bases, strings, quoted terms, and new lines. And with these sequences, we can already cover many use cases. However, there's a bit more to format underscore because we can use it for alignment, that is to align text, especially to align text in columns. For instance, suppose we have a database that relates a Prolog system to its implementation language and the number of stars on its GitHub repository. For instance, Scryer Prolog is written in Rust and currently has 1,419 stars on GitHub. And Tau Prolog is written in JavaScript and has 437 stars. And analogously for Trealla Prolog. So this is our database. And what we want is a formatted table that displays the data more nicely, like this. This is, at least in some respects, much more readable because it uses alignment. Specifically, we see here 3 columns. The text in the first column is left aligned, the second column uses centered text, and the text in the third column is right aligned. And with format underscore, we can easily describe such alignments. We achieve them by distributing spaces between tab stops. For instance, to describe a line in the table above, I used a tab stop at position 0, that is the start of the line, another tab stop at position 20, one at 40, and the final one at position 50. And the control sequences to get such alignments are tilde vertical bar with numeric argument n to set a tab stop after character n on the current line, and tilde plus with numeric argument n to set a tab stop n characters after the previous tab stop, or after the start of the line, because each line implicitly starts with a tab stop. So with these 2 control sequences, we can set tab stops at the desired positions. And tilde t means that spaces are distributed evenly between the 2 surrounding tab stops. What does this mean? Well, let's consider an example. Suppose we have a format string consisting of, first, a literal character, then such a tilde t sequence, then tilde 12 plus. This sets a tab stop at position 12. So that's the format string, okay? And since it doesn't refer to any arguments, we specify the empty list as arguments. And we are interested in the characters C's described here. So this is the string we've described. And just to make this clear, of course this works the same if we use tilde s to refer to a string in the arguments, and we place the string here as the first and only argument. This describes the exact same string C's. So let's see why we get the solution. Let's consider the string we're describing. And we know that there's implicitly a tab stop at position 0. That is the start of the line. And we've placed another tab stop at position 12, right? And we know that this string, which we are referring to via tilde s, must occur at the start of the string, right? Because that's where the reference appears as the very first control sequence in the format string. So one of these boxes is now occupied by a character. And what remains is this tilde t. And as mentioned, tilde t means that spaces are distributed between the surrounding tab stops. So in this case, the remaining positions between the tab stops are filled by spaces. And that's why we get 11 spaces at the end of the described string, and therefore 12 characters in total. And we get the various alignments by moving this tilde t. For instance, if we place it here at the start of the string, then we get right-aligned text. Because in this case, the text takes again one character, and spaces are distributed between the surrounding tab stops where the tilde t appears in the format string. And therefore the text is right-aligned. And if we place tilde t at both sides of the string, then we get centered text. Because the text again takes one character, and spaces are distributed evenly among the tilde t sequences, which means that spaces occur to the left and to the right of the text in this case. So this is what we mean with evenly, because multiple tilde t sequences can occur between tab stops, and spaces are distributed evenly, or at least roughly evenly, because as in this case, the text sometimes can't be centered exactly. But if it's possible to center it exactly, then it's of course done. And in fact, we can also specify the character that we want to use for this padding. So with this tilde backward syntax, we can specify the character C to be used. For instance, we may want to format a table of contents where we refer to a section and then fill the line with the character dot until, say, position 25, and have it followed by the page number. And we can plug in the arguments dynamically, and when we ask for the characters described here, we get this string where instead of space, dot is used for padding. Okay, now that we know how to get such alignments, let's describe the entire table with a grammar rule. With a non-terminal, say table, where we relate a list of such facts, one fact per Prolog system, to a list of characters. So if there are no Prolog systems, then we describe the empty string. And otherwise, if there's at least one such fact, represented by, say, a term of the form PLS of PLS, for Prolog system, language and stars, and possibly remaining facts RS, then we describe a line of text. And here, format underscore comes in handy. So now we express the shape of one of the lines in the table. So first comes the name of the Prolog system. And we represent the name of the system as a string. So we use the tilde-s control sequence to refer to the string. And we want the first column to be left aligned. So we pad the column with spaces using the tilde-t control sequence. And we pad the column to, as mentioned, 20 characters. So we place a tab stop at position 20. 20 characters after the start of the line. So this is the format of the first column. Now let's describe the second column. The text in the second column shall be centered. So we pad it with spaces to the left of the text, then the text, and spaces again to the right of the text. And the second column shall also span 20 characters. So 20 characters after the preceding tab stop, we place another tab stop. And now the third and last column, in which we want right-aligned text. So we place spaces to the left of the text and then the text, namely the number of GitHub stars, which is an integer. And we place another tab stop so that the third column has 10 characters. And finally, a new line. So that's the shape of one line of text in the table. And as arguments, we specify the Prolog system P, the implementation language L, and the number of stars S. So that's the string we're describing, followed by the remaining lines for the other facts RS. So this is our declarative description of the table. And we can collect all the facts above to a list of terms of the form PLS of P, L, and S, where the arguments stem from each fact, that is, the Prolog system name, the implementation language, and the number of stars. So we generate a list ls of such PLS terms, okay? This means that instead of reporting each fact over time on backtracking, which we call a temporal representation, all these facts are manifested in space, that is in system memory, which we call a spatial representation. This takes more memory and also allows greater flexibility, because now we can use this list ls and ask for the table we've described, which uses our own custom format. So we relate this list of PLS terms to a list of characters Cs. And as answer, we get the list ls as before and the list Cs, the characters of the table. So this is the table we've described, or at least its first few characters, which we see here. Okay, now this is of course not yet what we really want, right? Because at least eventually, that is, as the very last step, we actually want to emit the described characters on the terminal, right? Or write them to a file. And actually writing characters is a so-called side effect, because it's outside the declarative description. It's extra logical. So how do we do this? Well, there are several ways. Maybe most obviously, we can use the standard predicates put char with one or two arguments. So we can simply say use put char to output each character in Cs. And when we post this, we get exactly the table we wanted. So we see the table which we emitted using put char, and after the table, the answer substitutions as before, which the top level emitted for us. So that's one way to emit the table, by using put char. And we can use put char with two arguments to also specify a stream. So we can, for example, also write the output to a file. And it works, but it's not ideal. Because for efficiency, output is best written in larger chunks. That is, not each character individually, but more characters at once. So another way is to use the predicates format. They are almost like the non-terminal format underscore, but instead of describing a list of characters, they simply write the characters to the current output stream or to the given stream. And except for this difference, we use them exactly like format underscore. So we say we want to describe, or in this case rather output, a string. So we use the tilde-s control sequence, and the string we want to output is of course the list Cs of characters. So we specify Cs as the single argument. So that's a better way to write this because it writes many more characters at once. However, it also has a drawback, namely the list Cs must be manifested entirely in memory. So if we want to emit a very large table, then this could be a problem, because we may run out of memory when the table is generated as a list of characters before it's even written. And therefore, the best approach to actually emit the described characters is to use phrase to stream or phrase to file from library PO. And in our example, this means that instead of phrase, which we use to manifest the list Cs of characters, we use phrase to stream. So we no longer describe a list Cs, but rather we specify in the second argument the stream to which we want to write the described characters. So in our case, we specify user output to write to the system terminal. And in response, we get our table again. And this way really combines all advantages. We have a declarative description of the table, which we can test and reason about. And the writing part is very short, a single predicate call, and the writing is also extremely efficient. Or at least it can be made extremely efficient, because an ideal implementation of phrase to stream doesn't even generate the list, but rather writes each character or chunk of characters as it becomes known and then immediately reclaims it from memory, because these characters are only needed for output. Another useful predicate for describing output is called portrait clause underscore. And as the name already suggests, it describes formatted Prolog clauses as strings. For instance, we can say portrait clause underscore of P of x and y holds if f of x holds and g of y holds. So that's a Prolog clause, specifically a rule, and we use round brackets for the argument to make it valid Prolog syntax, and we relate this clause to a list of characters Cs. And in response, we get a formatted version of the clause using indentation, new lines, and also a dot at the end. So that's the non-terminal. And the corresponding predicate portrait clause emits the format clause directly on the output stream, which can be very useful because this means that we can use the standard predicate read to read the output as a Prolog term. And this is in fact often used in failure-driven loops where we are looking for a solution S and want to emit it as a Prolog term that can be read with read. And we want to emit all solutions, so we use false to force backtracking. So we sometimes use this pattern, but in general, it would be better to implement top-level features that let us do this more conveniently. And for instance, as mentioned, we can simply press A in Scryer Prolog and other systems and get all solutions nicely formatted as a disjunction. And nowadays, we're of course less and less interested in output on the system terminal, but rather we often want to generate output in web applications and send it over a network. So as an example, let's consider how a Prolog application can generate HTML. And the general principle remains completely the same. First and foremost, we describe the output. And DCGs are ideally suited for this. And again, format underscore can be a useful building block in such descriptions. For instance, take the frequently asked questions of the newsgroup Complang Prolog. They are described by a DCG non-terminal FAQ. And you can also download the program. Now, let's take a look at the code. Here it is. And with Scryer Prolog, we can generate the document from the description, simply by calling this predicate run. And run uses phrase to stream to write the described document to the current output stream. And this is the actual description of the document, the DCG non-terminal FAQ, which describes an HTML page. So it mainly collects all questions and answers from the database and relates them to the HTML document that we want to generate. And it also describes header information and closing tags. And here are a few additional non-terminals to complete the description, such as questions, answers, describing the actual list of questions and answers, and that's the main content of the document, and our own, in a sense, mini language so that we can easily state here's a new paragraph or a new list item and so on. So these are shorthand notations for common HTML tags. And we can easily relate such elements to actual HTML code. So in total, the DCG describes a list of characters that constitute a valid HTML document, and that document is then emitted. And for example, we see that when describing a link, format underscore comes in handy because we want to embed the link target in the generated HTML tag. And format underscore lets us, of course, easily describe this. And as already mentioned, we use phrase to stream to emit the document on standard output, but only as the very last step. So the actual output is only a single goal. The output is not dispersed over many different goals, because that would prevent declarative reasoning about the program. Because we cannot apply generalizations when output occurs in a program, because removing such goals has extra logical effects. So this is how we do it. We focus on a declarative description of the output and keep the extra logical parts as small as we can. And as long as we do this, we get the usual advantages. The ability to test and reason about the output, because we can ask the program what the output looks like by posting queries, and we can easily write test cases as queries. Flexibility in where and how to write the output. For example, we can write the output also to a network stream and so on, and we can also automatically translate the output, encode it differently and so on, because it's available as a Prolog term. And also very importantly, if such a separation between declarative descriptions and the actual output frequently occurs in Prolog applications, then it will also help to motivate Prolog implementers to strengthen declarative features in the systems. For instance, at least currently, no Prolog system implements phrase to stream as efficiently as possible. And it's easy to see why, because nobody uses it yet. And therefore it's not important to Prolog implementers. So what are we supposed to do? Are we to bend the knee to the limitations of Prolog systems? No, of course not. It should be exactly the other way around. Prolog systems should cater to what we want to do and support these use cases efficiently. And we want to describe output declaratively in order to get these advantages in our Prolog applications. So by using these features, even if they are not optimally implemented maybe, at least not yet, we can contribute to the development of Prolog systems by motivating implementers to work on these features. And all these non-terminals and predicates, format underscore, format, portrait clause underscore, and portrait clause, are available in library format in Scryer Prolog, Tower, and Trealla Prolog. So if we take a look at this library, here it is, then we see the list of all supported control sequences, which include several that we haven't discussed, such as tilde-u to write large numbers using underscores to group digits, and tilde-l to format large integers in such a way that at most n digits appear on each line, using underscores as continuation characters. Or just plain tilde vertical bar without numeric argument to place a tab stop at this position. And maybe even more control sequences will become available in the future, so please refer to the source code for the latest features. And the good news is that the library is in the public domain, so you can freely include it in your Prolog systems and of course also in your Prolog applications. And if you use it, then you automatically also contribute to the goals of the library, namely giving Prolog implementers an incentive to support lists of characters more efficiently, because all these predicates reason about strings, and of course to describe output more declaratively in Prolog applications. And in some Prolog systems, we can also use existing predicates to implement, for example, format underscore. For instance, in Prolog systems that support format, we can call, using the non-terminal call, an auxiliary predicate, say a format underscore underscore, with the format string and the arguments, and in that auxiliary predicate, in addition to these arguments, we can now reason about the list difference described by CS0 and Cs, and we define it using the predicate format, if available, where we can say we want to describe a list of characters as a list difference of CS0 and Cs using the format string and the arguments, okay? So if your Prolog system has such a predicate format, then we can use it to define the non-terminal format underscore very easily. And if you're an implementer, then I recommend that you either provide the format library in your system or at least this definition, so that at least format underscore is available as a DCG non-terminal to nicely describe formatted output.